So for that part D, the change in position is 8 meters minus 0 meters over 16 minus 0 seconds. And we should have that 0 here for the correct sig figs. 8 minus 0 gives us 8.0, which has 2 sig figs. 16 minus 0 gives us 16.0, which has 3 sig figs. But in this division step, we have the 2 sig figs for 8 over the 3 sig figs, 16. And we're going to divide that using the least number of sig figs to round our answer to 2. And so we should have 0.5 meters per second. And because it's a velocity, that means it's a vector, and vectors have directions. So it doesn't really tell us north, south, east, west, right, left. It doesn't give us any clear indication. We just know that it must be some positive direction. So I just put forward. You could just put in the positive direction if you wanted to be even more general. But since it's a velocity vector, we should give some kind of direction. So jumping back in from last time, this is how you would answer and solve part D for this graph, finding the average velocity for this skater. Any questions about part D? All right. For part E, it says find the skater's average speed. Speed is not a vector, speed is a scalar. So we need to think about how the distance is changing regardless of the direction. So we don't care about the direction, but we need to know how far it traveled in each segment. So if we look at the graph again, in this first portion, the skater's moving 4 meters. And then in the next portion, it's just standing still, so moving 0 meters. And then it's moving backwards here, but the direction doesn't matter for speed, but it is moving 2 meters in terms of its distance. And then it's motionless here for another couple seconds. And then it moves 6 meters in this last portion. So 4 plus 0 plus 2 plus 0 plus 6. We have to actually look at every segment for distance and speed because it's a scalar value. So if I scroll back down here, you can see for that distance or path length, I've just taken the 4 meters plus 0 plus 2 plus 0 plus 6. The zeros don't really have significant figures because it wasn't measured. We just said it didn't move. But for the other ones that were measured, if we look at the data that's given up here, they all had 2 sig figs. So we should, and they all went to the tenths. Okay, so we should be keeping that in mind. If we add 4.0 plus 0, 2.0 plus 0 plus 6.0, that adds up to 12.0. Since the measured values all went to the tenths, this 12.0 should also go to the tenths because we're doing an addition step. In the denominator, 16.0 seconds minus 0. The 0 is sort of irrelevant in terms of sig figs, but so the change is 16.0 seconds. So if we're thinking about sig figs, we should have 12.0 divided by 16.0. And this is where the sig figs can get a little bit tricky. Whenever you're doing addition or subtraction steps for part of the problem, you need to round that answer using the addition subtraction rules. And then when you're doing the multiplication step or division step separate, you need to round using those rules separate. So if you are paying close attention, you'll see all of these distances, the 4.0, 2.0, and 6.0, they each only had 2 sig figs. But because of the addition rule, all of them being precise to the tenths, we end up having 3 sig figs here. And the 16 has 3, and because that's also the change, it also has 3. So now that we're in this division step, division doesn't have any reference to decimal position, it's just total sig figs. So if I've got 3 on top and 3 on bottom, my answer should have 3. So we need this 0 to show that third sig fig. So in this case, it's kind of an odd situation, but it happens when you have a mix of adding and subtracting steps with division and multiplication steps. Your sig figs can change from step to step. So even though all these original positions were only 2 sig figs, because of the sig fig rules, we end up actually having 3 in our answer here for part E. So any questions about finding the average speed from the graph or about sig figs for D or E?
I have a question about how you got to 3 sig figs though. Like I'm still confused on that.
Sure. So in this problem, we've got addition and subtraction happening in this step. And then we've got addition and subtraction happening in this step, and we've got division happening here. And addition and subtraction has its set of rules, and multiplication and division has a different set of rules. So while we're doing the addition steps and subtraction steps, we have to use those rules. So the rule for addition and subtraction is looking at the level of the precision according to decimals. So this 4.0 is precise to the tenths. We ignore the 0. This 2.0 is precise to the tenths. And this 6.0 is precise to the tenths. So since they're all precise to the tenths position and I add them together, my answer needs to show precision to the tenths. So,
okay, thank you.
Yeah, with significant figures, when we're adding and subtracting, you could actually end up increasing or decreasing the sig figs because we're focused in terms of total, because we're focused on decimal position. So that helped clarify it for you, Jackson?
Yeah.
Okay. Then this last step, once we get to the division, now that has 3, so then my answer needs to have 3 because we're dividing and it's total sig figs for multiplying and dividing. Other questions? These kinds of problems where you have a mix of adding, subtracting, multiplying, dividing, those are the most complicated for sig figs. All right. If there are no questions on D and E, we'll move on. For number 4, in what situation might average speed be a better measure of motion than average velocity? So really the key is in this first phrase, if the total distance traveled is important, or you might even phrase that if the path length is important. If you need to know what the length of the path was, then that's when speed might be more valuable. If the path length doesn't matter and the direction does matter, then we want to use velocity. So the key word for velocity is if the direction matters, then we want to use velocity. If the direction doesn't matter and the total distance is important, then we want to use speed. So that's kind of the breaking point. We don't need direction. We just want total path length. That's speed. We do need direction and we don't care about the total path length. That's velocity. So it's just kind of scenario to scenario. If you're running laps around a track, you don't want to use velocity because if you're starting and stopping in the same place all the time, your displacement's always 0. And that doesn't really help you know anything valuable. But if you're actually tracking how much your path length is in terms of how many laps you ran, that's more helpful information. So distance and speed would be more valuable if you're running in a circular track. Velocity would be more valuable if you need to know something about the direction, like it is from south to north or east to west or something like that. Right. Couple other things then, if we, any other questions, I guess, before I move on? Any other questions on 4A and 4B? All right, let's move on to the last page then. These kinds of ranking questions are pretty common with College Board. Looks like you're all frozen. I hope you can hear me. Can you guys hear me? All right.
Yeah.
Yeah. Did I disappear for a while? You were all frozen for a few seconds. Okay, good. I'm glad. So just making sure you didn't miss anything. For ranking questions, these are common for College Board where they give you various scenarios and ask you to rank them. And they sometimes ask you to rank them from greatest to least or least to greatest, from positive to negative or negative to positive. They phrase it differently depending on the scenario, but these are good ones to practice. And I can pretty much promise you'll see some sort of ranking on the test next Thursday. So let's talk this one through. If we look down, here are the 6 objects, all with different kinds of motion patterns. And then part A wants us to rank the average velocity. So for velocity, remember, we don't really care about the direction changing. We just want to focus on displacement. So how far did it go from start to finish? Not in its path, but just straight line start to finish. And so here is the ranking. C is the most positive value because I ask you to rank it from most positive to most negative. Since it's a vector, then there are positive and negative values. Just to make sure you're clear though, this negative value isn't smaller in magnitude. It's not, it could be even the largest number. They're just asking us to rank it from positive to negative so that the ranking is clear since it's a vector. So C ends up being the most positive, D is the next most, F is next, A and B are tied, and then E is the most negative. The way I've filled in the blanks, since these were tied, I just skipped 5 and put that in 6. Just so you're aware, when they ask you for ranking, they don't usually give you blanks like this to fill it into. You actually have to put like C is greater than D is greater than F, like you use greater than and less than signs, or you write it in words, but they don't give you blanks to fill in generally. So don't worry about whether you should skip blank 5 or anything like that. That's not really going to show up when they give a test. Or even if I gave a test, if you just put in blank 4, if you had A here and B and 5 and you just put an equal sign between them or circled them and put equal or something, that's fine too. The key is, are you getting them in order? So let's go ahead and calculate the velocity for each and make sure we're understanding it well. So for object A, somebody unmute and tell me, what is the velocity, the average velocity for object A?
0 meters per second.
0 meters per second. It is not changing position, so it has 0 velocity. Somebody different, how about object B?
0 meters per second.
Also 0 meters per second. Good, it's not changing position. Someone different, object C.
1 meter per second.
1 meter per second. It goes 10 meters in 10 seconds. So that is a 1 meter per second velocity. And it's in the positive direction. So we should say +1 or 1 in the positive direction or 1 to the right, something like that. Somebody different. How about object D?
0.7 meters per second, I think.
Yeah, that is correct. 0.7 meters per second. It goes from 3 to 10. So that's 7 meters in 10 seconds. So 7 meters divided by 10 seconds is 0.7 meters per second. Somebody different. How about letter E?
-3/2 meters per second. -1.5.
Good. -1.5 meters per second. And the negative is important because it is moving in the backwards direction and velocity is a vector. So here we said 0.7. If we want to really be clear, we could say +0.7. And this is for sure -1.5 meters per second because it's going backward. So if we think about change in position, it's final position minus initial. So 0 meters minus 15. So we get a -15 change in position divided by 10 seconds. All right. For letter F, somebody else, what is the change in velocity, or the average velocity for object F?
Can I go?
Sure.
0.5 meters per second.
Good. How did you get that, Carter?
I just like drew a line in between the start and finish.
Good. So the fact that it goes up here to the 10, we don't really care about for velocity. We're just thinking about displacement. What's the final position? What's the initial position? And what's the exact difference between those two? We don't care about the path. So it ends up at 5. It started at 0. 5 minus 0 is 5. So it went 5 meters displacement. And that happened in 10 seconds. So 5 meters divided by 10 seconds is 0.5. So if we look at the ranking, C was the most positive because it is +1. D was next because it is +0.7. F was next because it's +0.5. And then A and B are tied because they were both 0. And then E is the most negative. It's the only one that was negative at -1.5. So if I was not talking about velocity, if I was just talking about magnitude, which one is actually moving with the largest magnitude?
It would.
I heard one vote for F. Do we agree? Are there any other thoughts? So magnitude is just the numerical value. Which one of those velocities had the largest numerical value?
Wouldn't that be C?
C is 1. Let me rephrase the question. What is the change the question actually? What does the positive and negative tell me on these velocities? Direction. So if I don't care about the direction, I just want to know which one's moving the most rapidly based on velocity. Okay, based on velocity, which one has the highest absolute value of velocity?
E and F.
For velocity, just E, right?
Oh, yeah.
Because F would be 0.5. So E actually, if I were just thinking about their numerical value, E actually has the largest numerical value. The fact that it's negative doesn't mean it's moving slower than the others. It just means it's moving backward. Okay, so if I'm thinking about which one's covering the most ground per second, it's actually E. It just happens to be going backwards. That's why it ranks last in this list, because it's said to rank it from most positive to most negative. So it's actually covering the most ground per second in terms of displacement. But it's negative, so it had to rank the least in this list. All right. Questions about that? I want to make sure you're understanding what the words mean too, not just the ranking. All right. If we see the reasoning, basically we're just focused in on, this is a displacement divided by time. So if you just take the displacement divided by time for each one and then rank them, and your displacement is final position minus initial position, so you end up getting a negative for that sample E. For part B, it says greatest average speed. And so for speed, you can see E and F end up being tied. They were not tied up here. C ends up coming in next, D next, and then A and B are also tied. And in this one, because it's speed, and speed is a scalar, there's no plus or minus. So it doesn't say most positive to most negative, because none of them can be negative. For speed, they can only be positive values, because speed is based on distance, not displacement. And distance is the path length, and it's always positive. So if we come up here to the graphs again, Atticus, what would you say is the speed for sample A?
2.5 meters per second.
No, it's staying at 25 meters.
Oh, sorry. So 0.
Yes, good. So it's going to be 0 meters per second because it's just staying in that position. So in this case, the speed and the velocity end up being the same. It was 0 velocity. It's also 0 speed. Jenny, what about part B? What would you say about the speed for object B?
0 meters per second.
Yeah, it's sitting at a different position, but it's still just sitting there at 5 meter mark. So still no change in position, so no distance or displacement. And so B also has the same speed and velocity. Those two numbers are actually both the same. Jilly, how about part C? What do you think about the speed for part C?
Um, 1 meter per second.
Yeah, and so that one is also the same, as the speed and the velocity end up being the same value. In both cases, it went 10 meters. The distance and displacement would both be 10 meters because it was going in a straight line. And let's see, Roy, how about part D? What do you think about part D for speed?
Well, wouldn't it still be like 1 though?
Well, it starts at 3.
Okay. I'm actually not sure about this one.
Okay. Can someone help him out?
Is it?
Was that Mark?
Yeah.
What'd you say?
0.7 meters per second.
Yeah, 0.7. So it's still traveling 7 meters of a distance in 10 seconds. So
Okay.
that makes sense?
Yeah.
So in this case, also, the speed and the velocity were exactly the same. So A, B, C, and D had the same speeds and the same velocities because in every case, their distance and their displacement were identical. Their path length and how far they were from their final position to their initial was the same. So A, B, C, and D all had the same speed as they had velocity, no changes. But E is where we're going to see a change. Frank, how about E? What do you think about E for speed?
For E is 1.5, a negative 1.5.
If it's velocity, it's negative, but if it's speed,
Oh, for speed is a positive. It's always going to be positive, 1.5.
Yeah. Good, good. So the velocity was negative 1.5, but now for speed, we don't use negatives. We don't care about direction. So it's just positive 1.5 or just 1.5. And so for E, the speed and the velocity have the same numeric value, 1.5. But for velocity, we say that it's negative because the velocity needs a direction and the negative tells me it's moving backwards. For speed, we don't care what direction it's moving. We just want the numerical value. And then for the last one, the tricky one, Jackson, how about F? What do you think?
It moves 15, or it moves like 15 meters over 10 seconds, so it'd also be 1.5 meters per second.
Good. So for this one, the distance and displacement are different. Therefore, the speeds and the velocity must also be different. The displacement, we said, it went from 0 to 5. So it just covered 5 meters displacement when we were trying to think through the velocity. But for distance, it goes 10 meters and then 5 more meters. So the distance, the path length is actually 15 meters. And so E ended up being 1.5 and F is also 1.5 when we're talking about speed. So you have to be really careful with speed and velocity. If it's speed, we're thinking about distance, which is the actual path length, always positive. If we're thinking about velocity, we don't care about the path or we just want to know how far is it from start to finish in a straight line. And then we do need the direction for that displacement, which means we would also use that same direction for the velocity. Down at the bottom where it gives that ranking then, the E and the F were both 1.5. C was 1, right? Yep, 1. D was 0.7. And A and B were both 0. So actually A and B are the smallest the speed could be, right? You can't have negative speed. So A and B at 0 are the smallest speed that's possible. For the reasoning, basically the idea here is that distances are scalars. Therefore, speed is also a scalar. And that means they can never be negative. We don't really care about the direction when we're doing distance and speed. Questions about this page?
Just to clarify, for F, for graph F, is it 1.5, the average speed? Okay.
Yes. Anything else you want to ask about? All right, so if you think about any one little piece, the fact that distance is the path length, that's not hard to know. The fact that speed is distance over time, well, that's not hard to know. The fact that distance must always be positive, that's easy to know. Speed must always be positive. Okay, that's not too hard to know. Like all the individual pieces aren't hard to understand. But where the complexity comes in is you have to know all those things at once. You have to know what exactly distance means and that it's always positive and that that's what we use to calculate speed, which means speed must also be positive. And so it's not like it's not isolated knowledge. It's a bunch of bits of knowledge tied together. And that's what brings the complexity. There's not like the math is not hard. 10 over 10 is 1, 15 over 10 is 1.5. It's not the math that's hard. It's keeping all those thoughts and keeping that train of thought connected. And that's what makes these tricky. So hopefully that makes sense. Any last questions before we move on? All right, I'm going to stop sharing that. That worksheet 3 again is due tonight. So I gave you that reminder before we started going over it that that's due on Access tonight. So make sure you're getting that taken care of. And now let's move on to the notes for the day. If you need to look back at these notes in the future, you can always find them on Access. They are in a PDF form. I show them to you using Smart Notebook, but when you look at them online, it's going to just be a PDF. And some of the slides might be moved around just a little bit. I've taught, this is the 3rd time today I've taught it. And every class I've tweaked something. I've like rearranged the order of 2 slides, or I've highlighted something in a color that wasn't highlighted before. Like I'm never quite satisfied. I'm always trying to make it just a little bit better. And sometimes there's like a student that will ask a question. I think, oh, I never thought about that before. And so I'll like underline a word or just some tiny little detail. So you might see some slight little details between this and what's in the PDF, but it should be really similar. Once we're done with the notes today and tomorrow, then I'll resave this as a new PDF and it'll match exactly, but you should still be able to find everything in that PDF on Access. And every day, every time I teach it, I always just think of one little thing that try to make it a little clearer, or sometimes it's taking a word away because it's less complicated, but I'm just always trying to tweak things to make it better. So it's that I'm never satisfied, but always content. So hopefully I can be content with where I'm at in life and the blessings God's pouring out of me, but I'm never satisfied. I always want to get just a little bit better. All right, so today we're going to have a lot of notes that are review. So I'll go through those pretty quickly. But then there's little nuggets of new bits that, as I told you before, we kind of spiral through and come back and revisit things with slightly different wording. And there's little bits that we haven't quite nailed down before that I want to nail down today as we wrap things up for Unit 2. So we've talked about position and reference frames. We did the whole tortoise and the hare discussion last time, where the tortoise was on the train and the hare was on the ground. But when we talk about frame of reference, there's really 3 things we want to make sure we're clear about so that there's no confusion. The first thing we need to be clear about is the origin. Where were we starting from? Because if one person thinks we're starting from the 0 mark and the other person thinks we're starting from where the object was, then there can be some real confusion about how far it went. So it needs to be really clear. What are we referring to as the origin? Is it really the 0 origin, or do you mean like where it was originally? So that's really needs to be clearly explained. What origin are we referring to? Typically speaking, if they use the word origin, they do mean the 0 mark, not necessarily where the object started. Okay, it could be the same, but not necessarily. The second thing we want to make sure we do is give a clear direction. And we will, in this unit, really only be working with 1-dimensional motion. So we usually just use the x-axis. Although on positive physics, you've seen that sometimes they choose to use the y when it's moving vertically. And that's okay, but we've only been working on 1 axis at a time in terms of analyzing the motion. But in the next unit, we're going to start looking at 2-dimensional motion. We never really get to 3-dimensional motion in this course, but you do need to specify what axis are we referring to? Are you talking about X, Y, Z? What is our direction, so that that's very clear as well. And then the third thing that needs to be clear is what unit are we using? Because if one person's talking about meters and the other person's talking about inches, then that can be really confusing. Even if it's just centimeters and meters, we need to be really clear about the units we're using so that when we're describing the frame of reference for something that's in motion, everyone is on the same page. So know the origin, know the direction, know the units that you're using to describe those measurements. Okay, those are the 3 elements you need to make sure for your frame of reference. Now, we've also talked about this before, but there's one new little twist I'm going to add. So it says we will be solving problems in 1 or 2 dimensions. This unit 1, next unit, we're going to add 2 dimensions. Typically, we use the x-axis for 1 dimension, so most of the time we're using that for our problems in this unit. And we usually say positive is to the right and negative is to the left, so that just matches the x-axis on a coordinate plane. Here's the new bit. We could define it the opposite way. And that is something I haven't mentioned yet. Or at least I don't think I have. Sometimes a student will ask and I'll bring it up, but I haven't intentionally brought it up until today. So while we usually think of right as positive and left as negative, you could for some reason say, you know what, I want left to be positive and right to be negative. Most of the time there's no need to do that, but especially when we get into two-dimensional motion in the next unit, there's occasions where it's a bit easier. Or if something is always in free fall, instead of working with a whole bunch of negative numbers, you could just define downward as positive and up as negative, and then you don't have to worry about all those negatives. So there are times where you can simplify things by changing your definitions. But you'll notice here there's a big but. Unless you specify, we assume right is positive, left is negative, up is positive, down is negative. So we assume it matches the coordinate plane directions unless you've specified otherwise. Okay, so you can define it another way, but you have to clearly specify that if you're defining it another way. And then it just reminds you here that it's the same for the compass directions. So north and east match the upward on the y and to the right on the x, so they're both positive. South and west match the backward on the y and the the backward on the x and the downward on the y, so those would both be considered negative. And we typically use the variable x for position, regardless of whether we're putting that on the x or y axis for our graphs. We usually use that variable for position. So mostly review, but this one little new concept that technically you can change the definitions if you would like. All right, in the chat, let's have you answer a couple quick questions to make sure you're getting it. So let me turn the chat on so I can see your responses here. So here's your first question. All of the following are examples of positive direction except. So unless it's defined otherwise, all of these would be positive except which one? Good. I see a bunch of people saying C or west, and that is the correct answer. All the other ones are positive. West would be negative. All right. All of the following examples are negative direction, except which one? Good. Unless it's specified otherwise, A to the right would be considered positive. South, west, and down are all negative. All right. Let's go back. So it's going to be kind of that way in the notes today. Little review, a few little nuggets, a couple questions to make sure you're getting it. All right. So here's the next concept, average velocity. And we've already done average velocity. We actually, on worksheet 3, we were just working on that a few minutes ago, finding the average velocities from those graphs. So it's not a completely new topic, but I just want to hash it over one more time. First, let's make sure we do clearly understand the difference between velocity and speed. So speed is distance versus time, this equation. Velocity is displacement over time, this equation. All right, so just this all should be in your notes somewhere already. We've had this speed equals distance over time. We've had this velocity equals displacement over time. We've had these definitions, but this is just one more time to hammer it home. While they are closely related, and at times their numerical value can even be equal, they are not the same thing. Okay, speed is distance over time, and it is a scalar because distance is a scalar. Velocity is displacement over time, and it is a vector because displacement is a vector. So for velocity and displacement, we should give a direction. For speed and distance, we do not. For velocity and displacement, they can be positive or negative, which is what the next slide is going to tell us and remind us about. But for speeds, they are always positive. Right? So again, a lot of review. Speeds are always positive. Since speed is the ratio of distance and time, and both of those are always positive, the speed must always be positive. Velocity can be negative or positive since velocity is the ratio of displacement in time. Since displacement can be negative or positive, therefore the velocity can be negative or positive. And then down here at the bottom again, notice the word usually. Usually, right is positive and left is negative. You could define it otherwise, but unless it is specifically stated, we assume right is positive and left is negative. All right, so speed and distance are scalars, velocity and displacement are vectors. So let's do a little checklist here. Scalars have both magnitude, a number value, and only a number value. Vectors have both magnitude, some number value, and a direction. Right? So which is time? Which one does time fall under, vector or scalar?
Scalar.
Scalar. All right. How about distance?
Scalar.
Scalar. How about displacement?
Vector.
Sorry?
Vector.
I heard something that was super quiet.
Vector.
Vector, there we go. I couldn't tell who it was. Speed,
Scalar.
scalar, and velocity,
Vector.
vector. So of the things we're studying right now in Unit 1, displacement and velocity are the only vectors. They are the only values that should ever be negative, right? They're the only ones that have an ability to be both positive and negative based on their direction. Time, distance, and speed are all scalars, so they will always be positive values. All right. So which one of these is a vector? Go ahead and put it in the chat. All right, good. We got a flurry of B's. Velocity is the only vector in that list. And then average velocity is defined as change in blank over an interval of blank. All right, in the chat, I'm seeing a flurry of C, and that is correct. It's a change, excuse me, a change in position over an interval of time. If we substituted distance in time, what would that be the definition for?
Speed.
Speed.
Speed, good. You travel 60 meters to the right in 20 seconds. What's your average velocity? All right, Jilly, nice. So Jilly, I saw a lot of 3 meters per second, and Jilly added the word to the right. Since it's a velocity, we want to indicate direction. Now, you might say, well, I put in 3 meters and 3 was a positive number, so it should be assumed that it's in the positive direction. For velocities, actually, College Board, for any vector, College Board really wants you to emphasize the direction, either with a word or a clear positive sign. So just writing 3 meters per second, while that is a positive value, that doesn't necessarily indicate that you know the direction is positive. So they would want you to put either the word right or a positive sign to emphasize that direction. An elephant travels 60 meters to the left in 20 seconds. What's the average velocity? All right, seeing a bunch of negative 3 meters per second, and that is fine. Or you can say 3 meters per second to the left. Either way is fine. You don't want to do both though. You don't want to say negative 3 meters per second to the left, because then they may be confused. Do you mean it's the opposite of left? What? So either use the sign or the word, one or the other, but not both. All right, you travel 60 meters to the left in 20 seconds. Then you travel 60 meters to the right in 30 seconds. What's your average speed? Anybody coming up with a different answer?
I got 2.4.
Yeah, so might just be a mental math mistake, but if it's 60 meters to the left and 60 meters to the right, we don't really care about direction for speed. So it's just 60 plus 60 is 120. And then 20 plus 30 is 50. So it's 120 divided by 50. So we should get 2.4 meters per second. Might just have been mental math mistake there. Everybody okay with that? All right. You travel 60 meters to the left in 20 seconds, then you travel 60 meters to the right in 30 seconds. Same scenario. What's the velocity? Average velocity. Good. So we're moving to the left, then we move back to the right. So if we go forward 60 and backward 60, our displacement is 0. If our displacement is 0, our average velocity also must be 0. All right. Now let's talk about instantaneous velocity. So we've just done average velocity. We've talked about instantaneous time, but this is going to be kind of a new concept here with instantaneous velocity. Sometimes average velocity is all we need to know. If we're talking about a straight line race like we see here in the picture, the average velocity will determine the winner. That's the, whoever covers that displacement in the least amount of time is going to be the winner. So for a straight line race, average velocity will tell us the winner. But it doesn't necessarily tell us who reached the maximum speed. Someone might actually have a higher top speed, but it took them longer to get there, so they don't actually win the race. Or maybe they got there and then they got too tired and they end up slowing back down. So the best maximum speed, or the speed at any particular point in time, doesn't tell you who wins the race. The average tells you who wins the race. So sometimes average is important, but other times we want to know instantaneous. If you're driving your car and you look at the speed limit sign and then you look at your speedometer, you want to know if you're going the right speed. You don't want to know your average. Your average isn't that helpful at that point. You need to know, how fast am I going right now? Because if there's a policeman, I want to make sure I'm not going to get pulled over, right? So instantaneous speed is sometimes more valuable. But here's the trick. There's no such thing as instantaneous velocity. So let's think about that. Velocity, someone give me the definition of velocity.
The
Displacement over
change.
time.
Carter, go ahead.
Displacement over time.
Displacement over time. Jackson, how are you going to say it?
The change of the change of x over the change of t, like so.
Yeah, good.
Displacement over time.
Good, yeah. So one gave more of a formula, one gave more words. Both are good. The key is it's divided by the change in time, right? How much time passed? Well, if it's instantaneous, 0 time passed. Can you divide by 0?
No.
No. So technically, there's no such thing if we're thinking about it strictly definition based, right? And yet we can look at our speedometer and know how fast we're going. So how does that work? How can we do instantaneous velocity when we can't divide by 0? So in physics, we have to come up with an alternate strategy, because we do know that if we see a policeman, we want to know what is our speed so that we know whether we're likely to get pulled over or not. Okay, so we know there has to be some way we can find some form of instantaneous velocity, even though technically there's no way to calculate it strictly by the definition. All right, so does anybody have any guess or idea based on other math that you've taken maybe? How could we find an instantaneous velocity if we can't just strictly take displacement divided by time when no time passed?
Is it like the derivative of? Yeah.
Okay, good. So for those that have had calculus, if you understand derivatives, that's what we're talking about. Can anyone expand on that or give another thought? Maybe for those that aren't as clear what derivative means.
The slope at any point.
Good. So we could look at the slope at any point. What is the slope of that line at any point on the graph, on that position time graph? All right. Now, next unit, we're going to focus on that second format of looking at the slope at any point in time on that position time curve. Today, though, I'm going to take a little bit of a different approach. And that slope and the derivative are that's the related concept. Those two things go together. But we're going to take a little bit of a different approach. Here's an example we'll walk through. So here at the thing, it says, in an experiment, an object travels at a constant velocity. So whatever we were doing, it was moving at a constant rate the whole time. And we measured its displacement after 100 meters. It took 10 seconds. So what was the velocity based on this data?
10.
10 meters per second, presumably in the positive direction, right? So, but what if we only measured the first 10 meters or the last 10 meters or the middle 10 meters? Well, if it was going the same velocity the whole time, if it could cover 100 meters in 10 seconds, it should cover 10 meters in 1 second, right? And that still gives us what velocity?
10.
10.
10, because it was going the same speed the whole time. Well, what if we made it even smaller? So we went from 100 meters to 10. We went from 10 seconds to 1. What if we made it even smaller? What if we went down to 10 thousandths of a second? Well, in 10 thousandths of a second, it would travel a thousandth of a meter if it's going the same rate. But what's the velocity in that case?
Still 10.
Still 10. Okay, so the idea is if we have something moving at a constant velocity for any length of time, and we narrow down that time span to a very small amount of time, that means it's going to move a smaller distance or have a smaller displacement. But the ratio is still going to give me the same rate. Could I get someone to read this part in red for us? Okay, Haley.
Since velocity is calculated based on change in time, we can't know the exact velocity at a particular time. But if we imagine a really small value of time and the distance traveled, we can estimate the instantaneous velocity.
So it's still true. We can't literally find an instantaneous velocity because that means no time passed, and therefore the delta t is 0. But if we make the delta t really, really small, then for all practical purposes, that rate would basically be an instantaneous velocity. Is it literally instantaneous velocity? No. But for practical purposes, is it close estimation? Yes. So here's another way that you might have heard it phrased in some of your math classes. Since we can't stop time, instantaneous velocity is determined by finding the magnitude of the average velocity if the time interval becomes very, very short. And in red, this phrase is something you may have already heard or you will hear probably in the future in your math classes as time approaches 0. Okay, so if you think about limits or as you're learning about derivatives, we think about as time approaches 0. All right, so it's not actually 0, but it's getting smaller and smaller and smaller. And so we're getting a reasonable estimation of instantaneous velocity by using an extremely small time increment. All right. Questions about that? All right, we'll keep moving. Last thing we want to cover is thinking about graphs and averages and how average velocity and average speed relate to each other. So this first one's pretty easy. The graph shows velocity versus time. What about this graph helps you know the velocity is constant?
Flat line.
Yeah, it's a horizontal line. So it's a velocity time graph. It is a horizontal line. Velocity is not changing. Super simple. All right, this graph is also velocity versus time, but is the velocity constant in this scenario? Clearly not. Yeah, it's changing. It's clearly not velocity. Or sorry, clearly not constant. All right, so let's see if you can interpret this correctly. So Atticus, if we look at this graph, from 0 to 1 second, so I'm just talking about this, like this little sloped part here in the very first segment, what can you conclude about the velocity there? Is it increasing or decreasing or constant in that first segment?
Increasing.
Increasing. And then Roy, how about this next segment, this plateau across the top?
This one's constant.
Constant. And then Carson, how about this segment where from this plateau down to the 0, what's happening to the velocity here?
Decreasing.
Decreasing. So pretty easy, right? I mean, we can see it's going from 0 to 4, so it's getting faster. It stays at 4, so it's constant. It's going from 4 to 0, so it's decreasing. Here's the tricky part. What about this segment going from 0 down to this plateau? What's happening here?
Changing direction.
It did change direction, but what's happening to the velocity itself? Is it increasing, decreasing, or constant?
Its magnitude is rising, I guess.
Yeah, it's actually increasing. But like Frank said, now it's just going the other direction. So even though this line continues from the top plateau down to this 0, it's decreasing in velocity, but moving forward. Once it crosses the 0, it's actually increasing velocity, but moving backward. Okay, so if you think about this like a car, the first segment, the car is going forward and speeding up, and then it reaches its cruising speed and stays at that cruising speed for a little bit. And then it starts to slow down and slow down and slow down, and eventually for an instant stops moving forward and starts moving backward. So maybe they were coasting up a hill and they got to the point where they couldn't coast any further, and now they're starting to coast back down, right? So now they're moving backward, but they're speeding up as they move backward, right? And then down here at the bottom, it's constant again. All right, so just being able to interpret those graphs and figure out where is it increasing, decreasing, and constant. So now back to the simple one. What's the average velocity given this graph?
1 meter per second.
Never changes, so the average is constant, right? But for this one, it's different depending on what time frame we're looking at. So what is the average velocity from 0 to 1 second, 0 to 4 meters per second? What's the average in this first segment?
2 meters per second.
2 meters per second. It starts at 0, ends at 4. 4 plus 0 divided by 2 is 2. The midpoint is 2, right? So the average in this first segment is 2 meters per second in the positive direction, right? Positive 2 meters per second. What's the average in this plateau across the top?
4.
Positive 4. It's 4 the whole time. What's the average from the plateau down to 0?
2.
2. Positive 2, right? It starts at 4 at this corner. It ends at 0. So halfway between 4 and 0 is positive 2. What's the average from 0 down to here?
Negative 2.
Negative 2. It's going from 0 down to negative 4, so the average is negative 2. Now here's the tricky one. So we just did 0 to 1 second, 1 to 3, 3 to 4, 4 to 5. What about from 3 seconds to 5 seconds? So they're saying, what about from this corner by the top plateau all the way down to this corner at the bottom plateau? What's the average on that whole span?
0.
0. Started at positive 4, ended at negative 4, so the average is 0. All right. Questions about interpreting velocity time graphs where it's changing? We've done a little bit of that, but this sort of ramps it up to a little bit higher level of difficulty from what we've done before. All right, let's keep moving. All right, so using this graph, what is the instantaneous velocity at 2 seconds?
1.
1 meter per second. It never changes, right? So at 2 seconds, it's 1 meter per second. It's 1 meter per second the whole time. Pretty easy for that one. Not too much harder here. What's the instantaneous velocity at 2 seconds?
4 meters per second.
4 meters per second. We just go to 2. Up at that point, it's moving 4 meters per second. So the real conclusion here is if we have something like example A, this top graph that has a constant velocity, if the velocity is constant, then the instantaneous velocity is the same as the average because it's not changing. But when we have something where the velocity is fluctuating, then that changing velocity means the instantaneous velocity may be different from the average. It depends on what instant we're looking at and what the average would be depending on which time frame we're looking at. So just making sure you understand that the instantaneous and average would be the same for constant velocity, but probably different in most scenarios if it's got a changing velocity. Any questions? All right, last topic, average speed. So we just went through an average velocity. We had positives and negatives. Now we're average speed. Everything's just positive, no direction. So with average speed, actually, let's just have, can I have someone read this first sentence here at the top?
I will. I can't speak. The speed we have been calculating in the sample problems is a constant speed over a short period of time.
And then Carson, would you read that second one?
If a trip has multiple parts, each part must be treated separately to calculate the average speed for a total trip.
Good. And then someone, the last one?
I can do it.
All right.
Determine the average speed by finding the total distance you traveled and dividing that by the total time it took you to travel that distance.
And this seems pretty straightforward. Total distance divided by total time. That should give me the average. But where it kind of can trip students up at times is sometimes students will say, oh, I'll just find the speed for this segment and the speed for segment 2 and the speed for segment 3, and I'll just average the speeds. That usually won't work. It won't work if the time frames are not identical. So we're going to look at an example and make sure that you understand why there's a difference by doing it total distance per time as opposed to averaging the speeds. So to set up our problem though, just a quick reminder, the following steps will help us. So we could think about the total distance as being distance 1 plus distance 2 plus distance 3. We just use these little subscripts to highlight that they're different segments. And then same for time, time 1 plus time 2 plus time 3. And then we take the totals. So this is the crux, this is the equation we're thinking of to try to find the average speed in a multi-step problem. All right, so here's our scenario. You ride your bike home from school by the way of your friend's house. It takes you 7 minutes, in other words, 420 seconds, to travel the 2,500 meters to his house. You spend 10 minutes there before traveling 3,500 meters to your house in 9 minutes, or 540 seconds. What was your average speed for this trip? So a couple things we can do. We can either do a diagram to help us think it through, or we can use a table. I'll show you both. Now, if you're really good at word problems, you might not need either one. But if word problems intimidate you or you often get confused as you're trying to solve them, a picture or a chart may help you. So let's do a picture first. Same scenario here, but we can say, okay, well, we started at school and we went to our friend's house. And that took, that was a distance of 2,500 meters. And it took 420 seconds. So that was the first part. That's like segment 1. And then after that, we stayed at our friend's house for 10 minutes. So we stayed at our friend's house for 600 seconds. And that means since we were just staying at their house, we traveled 0 meters, right? So we went to our friend's house and then we stayed there. And then we went home. And that took 540 seconds and was a distance of 3,500 meters. So we've got the first segment, the second portion, and then the third part, right? 3 different segments. So if we just think it's going to be distance total divided by time total, pretty easy. Add the distances, add the times, solve it, right? Pretty straightforward. But putting it together in a picture kind of helps us make sure we don't skip any part. So that's one way you could do it. If you're not great at pictures or you just don't like drawing it out that way, maybe use a table. Segment 1, we went 2,500 meters. It took 420 seconds. Segment 2, we stayed at our house, at our friend's house, so we didn't go anywhere, and that was for 600 seconds. Then we went 3,500 meters to go home. It took 540. So just organizing it into a table and then adding up your total distance and adding up your total time and dividing it and getting the average speed. Now, I haven't worried about sig figs on this problem because some of the numbers they gave us only had one sig fig. So that would be kind of rounding it off a little more than I want to for this example, but just wanted you to see through the logic of it. So that is how you could solve it using a diagram and how you could solve it using a table, if either of those strategies help. Any questions about that?
What happened if the question asks you to get rid of the second part of the segment?
Oh, if they just ask you to ignore that part?
Yeah.
Then you would just take out this 600 seconds from your total time.
Okay.
So you would just take 2,500 plus 3,500 divided by 420 plus 540.
Okay.
Good. Any other questions? All right. I just want to show you why it does not work to do average speeds. So if we took this divided by that, you get 5.95. I've struck it out because I want to make sure you understand this is a method that doesn't work. All right, so that's why it's got a line through it. That is the right number, but this is not the right method. If you take 0 divided by 600, you get 0. 3,500 divided by 54 or 540 is this. So if you average those, you do not get this. Okay, whether you add these and divide by 2 or add them and divide by 3, however you want to average it, you do not get this number. If you just take these two, you get 6 point something. If you take all three, you get 4 point something. You don't get the correct answer. And the reason you don't get the correct answer is because these three time frames are not the same. Since the time spans are not identical, you can't average the speeds, right? So you have to take total distance divided by total time to get the average speed when the time frames are not identical. You could do a weighted average. If you remember how to do a weighted average, you could do that, but I think that's actually more work. It's easier just to get total distance divided by total time. Questions? All right. Well, your assignment is to complete worksheet 4. You should find both the PDF and the document form on chapter 2 of Axis. You can print it, you can do it digitally, just like always. It's not due until Monday night, but I would like you to have it done when you come to class Monday, because I want to be able to check it and go over it in class. So if you don't have it done, even though you don't have to submit it by class time, I would like you to have it done by class time so we can talk about it and go over it together. After we're done going over worksheet 4 on Monday, we're just going to spend whatever left time reviewing for the test. I'll tell you details about the format of the test, how many questions, give you quite a few hints. There is also a review sheet on Axis in the chapter 2 unit. Unit 2 topic. So you could start going over that review sheet if you want to do some early prep for that upcoming test. You could start reviewing your notes. So, I mean, there's not going to be anything super surprising that I tell you Monday, but I'll just give you some more details on Monday about the format more than anything. So for Monday, have worksheet 4 completed when you come to class, and then you'll have to submit it by that night. So if you make changes during class, that's fine. You can just submit it later. Make sure, again, reminders that I gave you at the beginning of class, get registered for the AP exam by October to avoid late penalties. Register for the AP classroom if you haven't yet. Make sure that you turn in worksheet 3 tonight. It's due tonight. And if you need some tutoring, you can go to the school website, look on the student life page, and you can find tutors from the National Honor Society willing to help you in a variety of subjects. All right, that is all I have for you today. If you have questions, feel free to stick around online for a few minutes and ask them. If you don't have questions, you're dismissed, and I probably won't see you till Monday, so have a great weekend.
Have a good day.
Hope you get feeling better, Lily.
Thank you.
Thank you.
You're welcome. Hey, Jenny, did you have a question? Oh, maybe not.
Yeah, but it's kind of irrelevant. So.
Sorry?
Well, it's kind of irrelevant, but I just kind of wanted to ask. I was talking to a friend who took physics 1 like 2 years ago, and she was telling me that if you take physics 1, you might like just study a little more, and just like you can go take the AP Physics C mechanic test. And she also went to Oaks. So I was wondering, but I feel like she was really strong in math. I think she took like year. I was wondering if it would be easy to take mechanics if I just have like the physics 1 background.
Yeah. So the way the physics mechanics calculus-based exam works, it's actually the same content. It's actually less content. So we will cover all the concepts. We just won't use any calculus to solve them. So you'll know all the concepts, all the definitions, everything. What you would have to learn on your own is how you use the calculus to solve them as opposed to using the algebra. And technically speaking, for people who know calculus well, the average physics calculus exam scores are usually 15 to 20% higher than the average physics 1 scores because it's less material. Because we cover 3 more units that you don't have to know for the calculus part. So I have had students every year. I have had a couple students take both. They just wanted to take both and then hope they did real well on one. I've had more students, well, not very many, but I've had a few more students just choose to take the C mechanics. And so far, I think I've had 3 take it and all 3 got 5s. So, and we don't do any calculus in class, but they were all pretty strong math students and they were all in calculus BC while we were taking physics.
Okay, then maybe it's not for me. I'm in pre-calc right now, so.
Okay. Yeah, I mean, if you really put a lot of time in on your own, I think it's doable, but it would be, you would have to put in quite a bit of work on your own to get that calculus connection. Yeah, so it's possible, but probably pretty tough.
Thank you.
Yeah. See you, Jenny.
Yeah.
Hey, Frank.
Hi. So the things, there's another AP class, right? Like Jenny said, the AP Physics Mechanics.
Well, we don't offer it at Oaks, but it is a class that does exist, yes. And so there's a different test.
Okay. So kind of related to her question, do you know there's a AP subject, not AP subject, but there's a subject 2, SAT 2 test, which is physics, right? Do you think, like after I take physics 1, do you think I'm eligible to take SAT 2 physics?
I'd have to look at the content for that. I haven't looked at that in several years. So I think you would, I'm sure you would know most of what's on that test. They may cover a couple things that College Board puts into AP2. So I would just have to, I could look over the book with you and see, like let you know which parts we're not covering, but I would guess at least 80% of it will be covering. Maybe all of it. It's been enough years since I've looked at it that I don't remember for sure. And I don't have one of those books. But yeah, from the last time I helped a student do that, there was very little that they had to figure out on their own. We covered almost all of it in class.
Okay. Yeah, we can figure it out next time. Yeah.
Okay.
Not a problem. And yeah, I have another question. So, you know, today we talked about the instantaneous speed of, right? And I'm just kind of curious, how does the speed gun work?
They work in different ways. The older ones used sonar, and so it actually sent out a sound wave, and when it would bounce off the vehicle and come back, they could judge by how long it took to go there and come back and how far it was away, the speed that the car was moving. It's based on a concept called the Doppler effect, and we'll learn that.
I think.
Yeah, we'll learn that next semester. Now they generally use more lasers. So instead of using sound, they use light waves, and they usually get a little more precise values. And so it's still a reflective kind of technology with a different kind of, it's not really technically lasers, but it's a light wave instead of a sound wave that they use now. So electromagnetic radiation.
So that brings up my next question, which is like last time we talked about the baseball players, right? And the observer. What happened if right now on a train there are 2 baseball players throwing the ball to each other, and there's another guy who's holding a speed gun and on the train with them and testing the speed of that, and there's the other guy not on the train, on the ground, pointing at the baseball. Would both observers get the same speed, or
No, the one on the train would get the speed, like before we said on the train it was 50, and then off the train it looked like 70 because the train was moving. So the one on the train would see the 50, but the one off would see 70.
Well, so does that mean the speed gun automatically relative the baseball speed to the train?
Yeah, so the reason it is because the speed gun's also moving with the train.
Okay, that makes
So
sense.
yeah, it's also moving at that speed, just like the players themselves. But the one that's off the train isn't moving. And so, yeah, the way it works is the sound goes and hits and then comes back, or the light wave goes and hits and comes back. And so if the car's coming towards you, when it hits and comes back, depending on the speed of the car, it's going to come back either faster or slower than it went there.
Yeah.
And so by the difference in that time, they can estimate the speed.
Oh yeah, now I totally understand. Okay, thank you.
Yeah, you're welcome.
And my other question is for the quiz. I know on Access there's you already posted a quiz due practice, right? So I'm just
the review sheet.
The review sheet.
Mm-hmm.
So I remember last time we took a quiz, not a test, and this time's a test, which you will combine Unit 1 and Unit 2 together, right?
No, it's just a Unit 2 test. I just made the last one a quiz because it wasn't there wasn't that much information, and it's just difficult to give tests in remote setting. But this time I really feel like I need to give more of a full test because the content is, I think, a little bit more complex and a little bit more of it. So I want to give a little bit longer test. So we'll probably use the whole 80 minutes instead of just part of the class period. Yeah, I'm still wrestling with how exactly to proctor it so that it makes sense for you and for me. That's the tricky part. It's easy when we're on campus, but it's difficult in this scenario. So my latest idea is to do part of it online and part of it on paper, but I'm not happy with that. So I'm still trying to figure out some other options. So, but on Monday, I'll tell you what I'll have to figure it out for sure before Monday. And so Monday, I'll tell you, okay, this is exactly what it's going to be. Is it going to be half and half? Is it going to be all online or all on paper? But it will be an actual test grade. So it'll be a little bit longer, a few more questions, a couple of harder questions that are more like College Board and what I mean by that is, so we learn a lot of information, and then College Board doesn't just say, what's the definition of speed? They ask a question that tests whether you understand that definition by how you answer it. So they don't just ask you what the definition is. So you have to know the definition well enough that you can think of it in a completely new way.
Exactly.
So that's where the complexity comes in.
Yeah. I know that because for AP Bio, it's like pretty tough. Because it's quite different because like for last year's test, it doesn't match to our practice questions. Our practice question is so easy, but on test is so difficult on another level.
Yeah.
Same thing as right now in my pre-calculus honors class. It seems like the homework the teacher gave to us is really, really easy, but on the test is difficult. So it's really testing us the knowledge, like critical thinking skills, I think. Yeah.
If you start to look at those multiple choice questions on the AP Classroom and the topics 1.1 and 1.2, some of it covers material from our next unit. So that's not that helpful, but just so you can start to recognize how the questions are more complex, even just that can help you start to see, oh, okay, it's not just asking me to find the average speed from a very simple scenario like we learned in class. Now it's wanting me to take that and then do something new with it. And that's the tricky part is it's impossible for us with the limited amount of time we have to talk about every possible kind of question they could ask, because they can ask it in so many different ways. And so what I have to try to do is teach you very strongly the foundation. So then you have to be able to take that foundation and then creatively stretch it to a new scenario. And that's what makes College Board so tough. It's just impossible to cover every scenario.
Yeah, I completely agree. Like having a strong foundation is so important.
Yeah.
And my last question is, I think, are you the basketball coach?
I have coached the last 2 years. I don't know if I'll be able to coach this year because I'm teaching so many more classes. Because I usually only teach 5 classes, but this year I'm teaching 10. And so I just the time it takes for coaching, I'll probably help out just as a volunteer when I can. But I haven't been to any.
Are they practicing?
They just started this week with training.
With varsity or other teams as well?
I think he just invited the people that were playing last year to start coming in and training. I think they're mostly doing conditioning, like a lot of running and stretching and stuff. You could email Coach Wild and he could talk to you about whether it's open to other. I haven't been involved at all. I haven't
Oh,
been. Yeah, because I've been so busy with teaching. I met him
yeah,
for
I know.
lunch yesterday, just to visit with him, and he said that they just started this week, but he knew that with my teaching, I didn't have time to come and help. So.
I understand. Okay. Let's see what else. Oh yeah, so there's another question. Since you're the physics teacher, I was absent for my first period. I was feeling sick, and I was just kind of curious. So like, what are the policies? So if a student is absent in your class, what should the student do?
I think you just have to report to the attendance office why you were absent.
Okay.
So
I reported
I think it's
office.
Amy Greason is her name. Like if you search A Greason on the like Outlook mailbox or whatever, I think it's A Greason, Agreeson, something like that. And she's the one that manages all, or Mr. Choi. You could also email Mr. Choi. I think those are the two that mainly handle attendance.
Okay.
And they could record whether it was an illness or whatever.
Okay, so you have to report them. Okay, you can't just email the teacher and say you're sick, so I can come to your class. Okay.
Yeah, right. For the I mean, it's nice to email the teacher and let them know, but we can't change the setting on the attendance. All we can show is you were there or you weren't.
Like, why does it matter? Like, why? So if the teacher knows I'm sick, and why should I inform other of those attendance people?
Because I think if you have an excused absence, then it looks different on your transcript than if it's unexcused. And for the teachers, we don't decide that. All we do is just say you're here or you're not. And then in the main office, they decide whether it's excused or unexcused. And so if you have a bunch of unexcused absences, that shows up on your transcript, and then colleges see that. So you don't want to have a lot of unexcused absences. But if you report in and say, hey, I was sick, then they mark it excused, and then it doesn't show up on your transcript. So but they're the only ones that can make that decision.
Oh, I see. Okay, so far I only have one, which is this morning. Okay, I'll email them. Okay, Thank you for telling me. Yeah. Thank you.
No problem.
Okay, have a nice day.
Thanks, you too. See you, Frank.
Bye.